day 16. So I've started the box. McGreedy has locked McSkiddy out of ELF TH HQ admin panel by changing the password. To make it harder for McSkiddy to perform a hackback, McGreedy has altered the admin panel so that it uses a CAPTCHA to prevent automated attacks. A CAPTCHA is a small test, like providing numbers in an image, that needs to be performed to ensure that you are a human. This means McSkiddy can't perform a brute force attack, or does it? After the great success of using the machine learning to detect defective toys and phishing emails, McSkiddy is looking to McSkiddy is looking to us to help him to build custom brute force scripts that will make use of machine learning to solve the CAPTCHA that will then continue the brute force attack. There is, however, a bit of irony in having a bit of machine solve a challenge specifically designed to tell a human apart from computers. So, we're going to learn complex neural network structures. How does a convolutional neural network function? We're going to learn how to use a neural network for an optical character recognition. And then we're going to integrate neural networks into a red team tooling. So today we only need the VM that I've started, and there's a split screen, so you don't need an attack box, you don't need a VPN. You just start the box and you're good to go, so we can skip this. Right, so today's task, we're going to look at how the red teams use machine learning to help them with attack systems. Before we can start attacking the admin portal, we need to expand on some of the machine learning concepts taught in the previous tasks. Let's dive in. In the previous task, we looked at how neural network structures. However, most of these structures were fairly basic in nature, and today we're going to cover an interesting structure called a convolutional neural network, or a CNN. CNNs are incredible machine learning structures that have the ability to extract features that can be used to train a neural network. In the previous task, we used garbage in, garbage out principle to explain the importance of our inputs having good features. This ensures that the output of the neural network is accurate, but what if we could actually have the neural network select the important features on its own? This is where CNN comes to play. In essence, a CNN is a normal neural network that simply has the feature extraction process as part of the network itself. This time we're not just using maths, but combining it with linear algebra. Again, we don't need to dive too deep into the maths here to keep things simple, but we can divide our CNN into three main components: feature extraction, fully connected layers, and classification. We've actually already covered the last two components in yesterday's task, and the day before, as the simple neural network structure, so the main focus today is going to be on feature extraction component. CNNs are often used to classify images. While we can use them with almost any data type, images are the simplest for explaining on how the CNN works, and this is a CAPTCHA that we're going to try and crack. We'll be using a CNN to crack the CAPTCHAs. Let's use a single letter for the CAPTCHA as our image. The first question to answer is, how does the CNN actually perceive the image? The simplest way is for the computer to perceive the image as a 2D array of pixels. The pixel is the smallest area that can be measured inside the image. Together these pixels are what create the image. A pixel's value describes the colour that you are seeing. You can see two popular formats here. So we've got RGB. The pixel is represented by three numbers, 0 to 25, and these three numbers describe the intensity of the red, blue and green colours of the pixel. And then grayscale, this pixel is represented by a single number from 0 to 255. 0 means fully black and 255 means the pixel is fully white. Any value in between becomes a shade of grey.
You want just asking says. So we are not human today. I hope TDS is off.
It's not off. But yeah, we'll be humans, but we're going to be using a bot to pretend to be a human. Right, so the 2D image array, we start off with the top left and capture the value of each pixel, working our way to the right before moving down. So let's take a look at what this looks like for our capture. Now that we have our representation of the image, let's take a look at what the CNN will do with the image. So yeah, this step, we take the image, we do a couple of processing steps to it, like pixelize it, give it a grid reference, effectively like a load of indexes, and then we number them with the value of what's in the index. So convolution. There are two steps to CNN feature extraction process that are performed as many times as needed. The first step is convolution. The maths is about to get slightly hectic here, so take a deep breath and let's dive in. During the convolution step, the CNN's feature extraction, we want to reduce the size of the input. Images often have several thousand pixels, and while we can train the neural network to consider all of them, this will be incredibly slow and without really adding any additional accuracy. Therefore, we perform convolution to summarize the image. And to do this, we'll move a kernel matrix across the entire image, calculating the summary. The kernel matrix is a smaller 2D array that tells us where in the image we're currently creating our summary. This kernel slides across the height and width of the image to create a summary image. So you see here it's taking like blocks of 9 pixels, and then it translates them into 1. So as you can see from the animation, we stop at the top left of the image looking at the smaller 3x3 section. We'll then calculate the summary by multiplying each pixel value in the kernel. Then these kernel values can be set differently for different feature extraction. We're not limited on a single run. The values of the kernel are usually randomized at the start and then updated as the network is busy training. We say that each kernel run will create a summary slice. As you can see from the animation, by sliding the kernel across the entire image, we create a smaller summarized slice of the image. And there are a couple of reasons why we want to do this. As mentioned before, we can create a neural network that takes each pixel as input, but this would be an incredibly large network without any improved accuracy. The summary created by the convolution process still allows us to capture the image's important details without needing every single pixel. In our CNN's accuracy decreases, we can then simply make the kernel smaller to capture more detail during the input phase. The term used for this process is sparse interaction, as the final neural network won't directly interact with each pixel. If you'd like to learn more, you can read about it here. And then this is a well-done doc on the actual concept of how that works. So if we calculate the feature in one location in our image, and then that feature should be just as useful as the feature calculated in another location on the image, making use of the same kernel to determine the summary slice means that the condition is met. If we update the weights in one of our kernels, it will alter the summary of all the pixels. This results in something called a property of equivalence to translation. Simply put, if we change the input in a specific way, the output will also get changed in the same way. If you'd like to learn more, you can read about it here. So this is what is translation equivalence and why do we use convolutions to get it. That goes into the detail. That's funky. Cool, well people can read that in their own time. Right, so we're going to perform the summary extraction with several kernels to create several slices that are then sent to the next step of our CNN feature extraction process. So pooling, the second step performed is the CNN feature extraction process is pooling. Similar to convolution, the pooling step aims to further summarize the data using a statistical method. Let's take another look at our single slice, at how a max pooling will provide a summary of the maximum value. As you can see again, each kernel that we create summarized based on the statistical method for max pooling. This is finding the maximum value in the pixels. We could then also use a statistical method such as average pooling, which would calculate the average value of the pixels. So you see it's looking at each square, like each group of 4, and then it just takes the largest value. It's pretty simple. Right, so then that's basically it. How the CNN determines its own features depending on the network structure. This process of convolution and pooling can be repeated multiple times, and in the end we're left with the pooled values for each of our slices. These values now become the input of our neural network. So fully connected layers. Now that we have our features, the next step is very similar to the basic neural network structure that we used back in the introduction to the machine learning task. We'll create a simple neural network that takes inputs, summary slices from our last pooling layer, run them from the hidden layers, and then finally provide an output. This is called the fully connected layers portion of the CNN. And at this point in this part of the neural network, where each node is reconnected to all the other nodes in the next layer. Classification. So lastly, we need to talk about the classification portion of the CNN. This is the output layer from the fully connected layers portion. In the previous task, our neural network only had one output to determine whether or not the toy was defective, or whether or not an email was a phishing email. However, to crack CAPTCHAs, a simple binary output won't do. We need the network to tell us what the character and later the sequence of characters is. Therefore, we need an output node for each potential character. Our CAPTCHA example only contains numbers, not letters, so we need to output a node for 0 to 9, totaling 10 output nodes. Having multiple output nodes creates a new interesting feature for our neural network. Instead of simply getting one answer now, all 26 outputs will have a decimal value between 0 and 1. We'll then summarize this by taking the highest value as the answer of the network. However, nothing is stopping us from reviewing the top 5 answers, for instance, and this can help us identify areas where the neural network might be having issues. For example, we could have a little confusion between the characters of M and N as they look similar. Reviewing the output of the top 5 nodes will show us that this might be a problem. While they may not be able to solve this confusion directly, we could actually use this to our advantage and increase our brute force accuracy. We can do this by simply discarding the CAPTCHA if it has an M or an N and requesting another CAPTCHA to avoid the problem. So training the CNN. So now that we've covered the basics, let's look at what will be required to train and use our own CNN to crack the CAPTCHA. Please note that the following steps have already been performed for you. The next steps will be to perform in the hosting the model section. However, understanding how the training works is an important aspect, so please follow along and attempt the commands given. We'll be making use of the attenuation OCR for our CNN model. The CNN structure has a lot more going on, such as LSTMs and sliding windows. We're not going to dive deeper into these steps in this instance. The only thing to note is that we have a sliding window, which allows us to read one character at a time, instead of having to solve the entire CAPTCHA in a single go. We'll be 22, which is a Python pip package that can be used to host a CAPTCHA cracking server. Let's check that out. Da-da-da-da. This is cool. I could actually use this for that license plate detection, because one of the tools for getting insurance details. So ask mid. So they've got the Google reCAPTCHA. So maybe I could look into this at some point. Right, and then so that's reCAPTCHA. It's a Python pip package that can be used to host CAPTCHA cracking server. If you're interested in learning how it works, read this here. While you can try to run the software yourself, most machine learning components run on a very specific version of TensorFlow. Therefore, making use of the VM attached to the task is recommended. In order to crack the CAPTCHA, you'll need to go through the following steps. Gather the CAPTCHAs that we can create labeled data. Label the CAPTCHAs to be used in supervised learning model. Train our CAPTCHA cracking CNN. Verify and test our CAPTCHA cracking CNN, export and host the train model so we can feed the CAPTCHAs to solve, and then create and execute a brute force script that will receive the CAPTCHA, pass it on to be solved, and then run the brute force attack. So steps 1 to 4 are quite taxing. They've already been completed for you. We'll do a recap of what the steps involve before moving on to the hosting model and cracking some CAPTCHAs. To do this, you just have to start the Docker container, so in a terminal window, execute the following. So terminal. Okay. Right, so we run docker run d v tmp data tempdir space and then aocr full. Which doesn't work, sweet. Right, see again. So docker run -d v temp data. I missed a slash, there we go. That's better. Right, so this will start the Docker container that has TensorFlow and AOCR already installed. You'll need to connect to this container for your few next steps. So first you'll need to find the container ID using the following command. So docker ps Let's make it wider so we can see everything. Just about get it all in. Right, so we've got the container ID. Take note of the ID and then follow the command. So that's the ID. So copy you. And then we'll run docker exec it, paste the container ID, bin/bash. There we go, so now we're connected. This connects you to the container. You can navigate into the following directory using cd ocr. Gather the training data. In order to train a CAPTCHA cracking CNN, we need to have created the dataset that can be used for training. Let's take a look at the authentication port for HQ admin. So open, copy link. Right, there we go. So we've opened that and now we can see the following authentication page. As we can see, the authentication portal embeds the CAPTCHA image, and we can get the raw image using a simple curl command from the normal terminal window. So we'll curl the whole main website. So go back to your terminal. Actually, I misplaced it. Okay. Could not resolve host. That's not very good. Okay, right. Fantastic. Let's do it from the local host then. Does it work from here? It does. So we can get it there. Right, so in the output you'll see the base64 encoded version of the CAPTCHA. Then we can write the script that will download this image and prompt it to provide the answer for the CAPTCHA to store in the training dataset. This has already been done for you. You can see the stored data using the following command in Docker. So let's go back to the Docker one. Run that. So there's all the files. So next we need to create the dataset and in a format that the AOCR can use. This requires using a simple text file that lists the path for each CAPTCHA and its correct answer. The script that was used to create the text file can be found under the labeling directory. You can use the following command to view the text file that was created. So cat labels training.txt. So there you go. So you can see they've got the file and the folder it's in, and then the answer to that. So you can basically do like a one-to-one comparison. So once we have the text file, this can be converted into a TensorFlow record that can be then used for training. This has already been done for you. You can use the following command to create the dataset. Let's just run that anyway. So as mentioned before, this has been done for you and stored in the labels directory. We've created two datasets, one for training, one for testing. As mentioned in the introduction to the machine learning task, oh, it failed anyway. We've created two datasets, one for training, one for testing. As mentioned in the machine learning task, day 14, we need fresh data that our CNN has never seen before to both test and verify that the model has been trained accurately and hasn't been overtrained. Just as in the previous task, we'll only use the training dataset to train the model and then the testing dataset to test its accuracy. So to train it, we can then start training the model, and this has already been done, okay? But with all the preparation completed, you would need to be able to use the command to start training. So we go into the labels directory and then run OCR train training TF records. Training then begins, and once you have completed a couple of the steps, stop it by doing Ctrl+C, and let's take a look at the output lines from running the training. So let's do this anyway. Let's do cd labels. and then AOCR training.tf records. So that's going to run, and then we can stop it. So looking at the output of one of the lines, so we've got each of the step, the CNN is trained on all the inputs, similar to what we discussed in the introduction to machine learning task. Each image was given an input to the CNN. We then made a prediction on the numbers that we present in the capture. We'll then provide feedback to the CNN on how accurate its prediction was, and this process is performed at each image of our training dataset. To complete one step of training, the output from the OCR shows us how long it took to perform this round of training and provides feedback on the loss and perplexity values. So loss is the prediction error rate. The closer to 0, the smaller our prediction error. If you were to start training from scratch, the loss would be incredibly high for the first couple of rounds until the network was trained. Any loss value between 0.005 would show that the network has either completed its learning process or has overtrained on the dataset. And then perplexity. So this is how uncertain it was with its prediction. The closer the value to 1, the more certain that it was correct. Considering how perplexed the CNN would be seeing the image for the first time, seeing something new would be perplexing, but as the network becomes more familiar with the images, it's almost as if you can't show it anything new. Any value below 1.005 is considered trained or overtrained. As the CNN has already been trained for you, you can now test the CNN by running AOCR. That's basically what I ran anyway, so we can run it without quitting it. So change training to testing. Now it's testing it. So once a couple of steps are complete, you can stop it again using Control-C, and we'll take a look at some of the lines. As you can see from the testing time, running the single image sample through CNN is significantly faster than training it on the entire dataset. This is one of the true advantages of neural networks. Once the training is completed, the network is usually pretty quick to perform the prediction. As we can see from the predictions provided at the end of the lines, one of the capture predictions was completely correct, whereas the other one was a prediction error, mistaking a 5 for a 6. If you compare the loss and perplexity values of the two samples, you'll see that the CNN is uncertain about its answer. We can actually see this, we can use this to our advantage when performing a live prediction. If we create a discrepancy between capture prediction accuracy and capture submission accuracy, simply by not submitting the captures, then we are too uncertain about. Instead, we can request a new capture, and then this enables us to change the OPSEC of our attack, as the log won't show a significant amount of entries for incorrect capture submissions. We could even take this a step further and save the capture images that were incorrect on submission, and then label them and manually retrain the CNN to improve the accuracy. This way we can create a super capture cracking engine, and you can read more about the process here. Releasing the Kraken. Yeah, this is a lot like the image, like computer vision stuff we were doing. Cool, so hosting our CNN model. So now that we've trained the CNN, I need to stop it as well while I remember. Stop. So now we train the CNN, we'll need to host the CNN model to send it captures through our brute forcing script. For this we'll use TensorFlow serving. Once the CNN has been trained, we can export the weights of the different nodes, and this allows us to recreate the trained network at any time. An export of the trained CDN has already been created for you under the OCR model directory. We'll now export that model from the Docker container using the following command. So there we go. Once that's complete, you can exit the Docker terminal using the exit command or kill it. We'll just leave it open. We'll use this box instead. So you can reuse the Docker PS ID. Oh, so it does actually want us to kill it. Alright, never mind. So, exit. Should still have my... No, I've so... Oh yeah, I do have it there. I deleted it anyway, bollocks. I was going to try and get the code out of it, but yeah. Docker PS... Right, Docker kill container ID. Right, TensorFlow serving will run in a Docker container. The Docker will then expose an API that we can use to interface with a hosted model to send it CAPTCHA for prediction. You can start serving the container using the following. So let's grab that. This will start a new hosting of the OCR model that was exported from the OCR training Docker container. We can connect to the model through the API hosted on that. Let's copy the link. There we go, so we've got the API. Right, now we're finally ready to help McSkiddy regain access to the HQ admin portal. We're going to brute force the admin portal. You're provided with a custom script that we'll use, which you can find in the custom script and password list on the desktop. We'll take a look at the folder. So, minimize these, brute forcer. Cool. So we've got username admin, blank passwords, link to the website, link to the model. Load in all the passwords from the txt file. Then, while we don't have access granted, and we have more than one password, then it will run beautiful soup past the web page, and then use the model to predict a password, or yeah, a CAPTCHA even. And then if it's got lower than 90% probability, it doesn't predict, otherwise it will submit the CAPTCHA. So that's basically that. Right, so let's run the brute force attack and then copy this. That's going. So this will run for a minute or two, and at some point we'll regain access to the admin portal. There we go. Not going to guess this. So in conclusion, in this task we've shown how machine learning can be used for red teaming purposes. We've also demonstrated how we can create a custom script to perform tasks such as brute forcing, like either authentication of a web app. All we need is a spark of creativity. While we have taken a pre-trained model such as the Tesseract OCR, it wouldn't have been nearly as accurate as the one trained specifically for this task at hand. This is true for most ML applications. While generic models will work to some degree, it's often better to use a new model for the specific task that we're tackling. And this is what I found when I was doing the number plate recognition. So it does work, but then it seems to capture, because it's trained on number plates that aren't from the UK, it will get like some part of the number plate, and then it would capture the bottom part of the car rather than just being the number plate. So then that's why I had to give it new data and retrain it. So cool. So now that we've had a task of what's possible, the sky is the limit. The key process of training a neural network is taken care of using a CNN. Oh, sorry. What key process of a training neural network is taken care of by the CNN? This is the feature extraction, or yeah, I think feature engineering. Yeah, there we go. What was the name of the process used in CNN to extract features? I have no idea. I can't remember. Just read it. Convolution, that's the one. I can't even remember people's names, let alone things that I've just read. Right, this is the name. What's the name of the process used to reduce the features down? This was pooling. OCR model. That was Tesseract. OCR. Let's spell it correctly. It's the one they used. Attention OCR, that's the one. What was the password that McCready set on the admin portal? So we go back to the terminal, captured that. What was the value of the flag that you received when you successfully authenticate to the admin portal? So we need to actually log in. View, get rid of view, and go into there. Admin. Password, capture 64395. There we go. CAPTCHA can't hold me back. So if we hope you've enjoyed the room, check out the red teaming learning path. This one's definitely a sub. So yeah, we've done a couple of these, but yeah, check that out. And that is all you get